Greetings and welcome to experiment number 4 of Mechanical Systems Analysis Laboratory. In this particular experiment, we are going to understand this programming of heat transfer analysis in PinFin, that is called as CFD analysis. But CFD means we are writing the code for heat transfer analysis to a PinFin. The content of this first in the introduction section, we will see the basics of heat transfer in a very brief. Then the theoretical analysis when the heat transfer is taking place through a fin, generalized fin. Then discretization, because the aim of this experiment, again, like previous experiment, is not to understand the theoretical concepts, but how to do the analysis numerically. So in this particular experiment, we are solving the differential equation using finite difference method. And in finite difference method, the central difference method we are using. There are three methods in finite FDM: central difference, forward difference, and backward difference. But central difference is more accurate method. Is the most accurate amongst all. So the discretization part we are going to learn this case. Then how to write the Scilab programming for this heat transfer analysis. That is heat flow analysis, we can say. The temperature variation along length of, we are considering the three materials for investigating the temperature variation along the length of the fin. So that variation we are going to understand or see. Then finally, result discussion and conclusion. The term extended surface is commonly used because extended surface is used to enhance the rate of heat transfer. And in this particular extended surface, it depicts all modes of heat transfer. There is all modes of heat transfer involves conduction, convection, and radiation. The conduction is within the solid boundary, and convection and radiation is between surface and the surface of the solid boundary and surrounding. So these are the various extended surfaces used in practice, and according to their shapes, they are called as if the shape is rectangle, this is called as a rectangle fin, this is triangular fin, this is annular fin, and this is a pin fin with non-uniform cross-section. So there are different fins used, especially to enhance the rate of heat transfer from the surface. And it is more efficient when the natural convection is used. For forced convection, it gives a lesser efficiency, but it is more efficient in natural convection part. As far as the heat transfer analysis through extended surface is concerned, if we consider this is the base surface and this is a non-uniform cross-section fin is attached to that, which is called as the extended surface. And for heat transfer analysis, we consider a small elemental area or ring, we can say. So of area dAs, that is for surface area, and cross-sectional area is AC. So if we consider the heat balance, so heat entering into this control, so we consider this as a control volume. Heat entering in this control volume, that is equal to heat dissipation. So entry is Qx, that is equal to Qx plus dx, and dq, that is heat transfer due to convection. And this is heat transfer within the solid boundary, that is conduction plus convection. So radiation part is mostly neglected because radiation part is considerable from the surface. If the temperature exceeds 100-150 degrees Celsius, then radiation part plays. But during analysis, to avoid complications, we consider only a convection part. Now, according to Fourier's expression, Qx is equal to minus k dt by dx. Here, A is the heat transfer area, which is available for conduction. So this is pi by 4 d square for fin. Then Qx plus dx, that we obtain using Taylor's expression, that is f of x plus f dash of x dx. So this is heat transfer available at the other end of this particular disk. And if we substitute Qx value here and simplify, then convection heat transfer where the area is different. This is a surface area available for convection. So that is HA delta T. So delta T is in this case is T is the surface temperature at any particular point, and T infinity is the surrounding temperature. So that is T minus T infinity. This is dq convection. So by putting all these values, so these three values, we can say, oh, this is qx here, qx plus dx and dq. So we can arrive this equation because in this differential form, the cross-sectional area is also varying along the length. So that's why area is also variable. And if we again differentiate this part and divide by AC, so we arrive this equation is equal to 0. But generally for uniform cross section, the middle term vanishes because dAc by dx, if there is no variation of area of x direction, then this is 0. So we can have d2t by dx square minus hpk. P is the perimeter. So instead of this, we can write a perimeter, surface area divided by x. This is called as a perimeter. So this part is called as a perimeter. So instead of this, we can write T. So Ka AC into T minus T infinity. Now T minus T infinity is the temperature difference at any particular point between, this is temperature difference between the surface and the ambient. So this term we call as a theta. So d theta is equal to again dt. So if we replace this T by theta, then the same expression we can write, that is d2 theta by dx square minus n square theta, that is equal to 0. So in this case, theta is the temperature difference, T minus T infinity. So this is the second order differential equation in terms of theta. Now the solution is very difficult analytically. So generally the numerical approach is used to obtain the solution because again the boundary conditions are slightly in differential form, second Newman boundary conditions. So that's why it is very difficult to solve this ODE equation analytically also. So numerical approach is used. Now in order to use this numerical approach, now this is the equation we have to solve now. Now this equation is applicable for this fin. So fin length is varying from 0 to XL. So XL is the length, we can say, and X value varies from 0 to also 0 at this side and L is that this side. Fluid temperature is T infinity, Q convection. Now the boundary conditions are if X is equal to 0, that is at the base, we can say, and is theta is equal to theta B. So theta B is the temperature difference, that is base temperature minus ambient temperature. Suppose if the base temperature is 100 degrees Celsius, ambient is 25 degrees Celsius, then theta B is 75 degrees Celsius, like that. So this initial condition is given. Then at X is equal to L, we can say the conduction part is equal to 0. Suppose if fin tip is insulated, we can say. So there is no conduction from this surface. Or we can say K dt by dx is equal to 0. So dt by dx is equal to 0. Consequently, d theta by dx is also equal to 0. So that boundary condition you already done. Now we have to solve this particular equation using these two boundary conditions. But this boundary condition, the problem is here. We cannot use ODE solver if the boundary condition is in differential form. So that's why we take a help of finite difference method. So according to finite difference method and that to central difference method, we can have we can discretize this equation, this particular derivation, double derivative. D2 theta by dx square at x is equal to xi, that is equal to theta I plus 1 minus 2 theta I plus theta I minus 1 divided by w square. So this is according to the central difference method. So for detail, you can Google it. You will learn what are the expressions for central difference, forward difference, and backward difference. This is the expression for central difference. So d2 theta by dx square is n square theta. So here we can write n square theta I. And if we resolve it, this is instead of this, we can write n square theta I. And if we put there and resolve it, we get this expression that is theta I plus 1 minus n square or w square plus 2 theta I, but plus minus into bracket, this is minus plus theta I minus 1, that is equal to 0. So this is W. W is actually a step size, we can say. And we will see how the W. This is the expression of theta in terms of I. So I values are different intervals, we can say. So we take 6 steps. Suppose this is 1, 2, 3, 4, 5, 6, and 7 nodes are there. So x is equal to 1 to x is equal to 7. 7 nodes are there. So accordingly, we can have a step size that is x1 minus x7 divided by 6. So each step size equal to L by 6. So this is L by 6. This is 2L by 6. This is 3L by 6. This is 4L by 6. This is 5L by, sorry, this is a printing mistake, 5L by 6. And this is 6L by 6 is, suppose, is L. So this is, understand this printing mistake. It's not 6, it is 5L by 6. So the step size is L by 6. So this way we get the values of each x from the linkage. So x values we have defined. Now by putting the values of I, so now we take the value. This is I is equal to 1 to I is equal to 7. So from 2 to 7, if we write, so instead of I, if we put 2, then we get this expression in this. So similarly, if we put other values, we are arriving this equation. Now let P is equal to this bracket term we called as P. And after substitution, we get this expression. Call this equation number 1. Now this is the set of equations for different values of I. Now we'll discretize this also, theta by d theta by dx at x is equal to xi. Now for x is equal to xi, we can call, suppose this is a theta I, then d theta by dx is nothing but theta I plus 1 minus theta I minus 1. And the step size is, this is 2w. So this is the equation differential form. But at x is equal to 7, we get x is equal to 7, we get 7 plus 1, theta 8 minus theta 6 divided by twice w. And this is theta prime 7, because theta d theta by dx is equal to theta prime 7. We can call this. So theta prime 7, that is equal to theta 8 minus theta 6, because 7 plus 1 is 8 and 7 minus 1 is 6 divided by 2. Now, if we resolve for theta 8, we can have this equation. Now, if we put theta 8, this is equation number 2 and this is equation number 1, suppose we can have. So by putting here, instead of theta 8, if we put this and resolve for theta 7, so we get theta 7, because theta 7 is the boundary condition or the value of theta, like theta value at 0, x is equal to 0. It is, so what is the value of theta at x is equal to L? So we are getting this expression. Now again, at x is equal to L, that is at theta 7. So x is equal to L, theta is equal to theta dash. Theta dash is z, theta, so sorry, theta prime 7, which is equal to d theta by dx, that is equal to 0. So this term is 0 at x is equal to 7. So, and if we put here 0, and if we put, instead of this, if we put the p, so the equation of theta 7 is 2 theta 6 by p. So this is the equation of theta 7. Now we have converted all the boundary conditions, these boundary conditions, into a integer boundary condition, not a differential boundary condition. And all the equations we have, this differential equation we have read, all these are the integer set of equations. Now we have to solve these equations using, now if you see, this is theta 7 dash, and we have theta dash is equal to 0 and p is equal to this, we get that expression. So equation 1 can be written like this in terms of p. This is set of equations. So 6 equations, sorry, 5 equations we have considered. Because we have to obtain the value of, already theta 7 we have, and theta 1 is already we have. So we'll eliminate the last equation because of that equation. Now the same equation we can write in matrix form. Now in matrix form, we'll consider the coefficients of only theta 2 to theta 6, because theta 1, which is equal to theta 0, and theta 7 we know. So no need to use the coefficients of this. This is a coefficient matrix. Now if we see the coefficients of first equations, so that is theta 2 is equal to minus p, theta 1 is equal to, so theta 1 we are not considering here because it is already given theta b. So theta 2 is equal to minus p, theta 1 that is equal to theta 3 is equal to 1, and remaining theta 4, theta 5, theta 6 is 0. So these are all the values. Similarly here, if coefficient minus p is for theta, these things, so theta 3. Then next equation coefficient is for theta 4. Coefficient minus p is for theta 5 here. And the last one, that is theta 6 coefficient. Here we can put, instead of theta 7, if we put 2 theta 6 by p, and if we resolve this, now it is 2 by p minus p. So coefficient of theta 6 is 2 by p minus p. So this is coefficient of theta 6. And only theta 5 coefficient is 1. And remaining all absent, that is theta 2, theta. So this is the coefficient matrix we can write from this set of equations. And this is the unknown variable, that is we have to get the values of theta for at theta from 2 to 6. And finally, on the right hand side, that matrix we can write. So only theta 1 we take on right hand side here, which is equal to minus theta b. So that equation we can take, that is minus theta b. And remaining values on right hand side is all are 0, 4. So this matrix we call as A into theta, that is equal to this matrix we call as a B. So theta is equal to A inverse B. Now we have to obtain the solution of this particular matrix, and we have to write the code for this matrix. So that is our aim. So now we write the Scilab code for this for solving this matrix. Now in this case, we are solving ordinary equations using finite difference method. So first we clear, this is a basic command. So all we clear screen as well as clear all figures in the Scilab console. Then the given information, in this case, we require heat transfer coefficient, because in order to calculate M value, that is HP by K, so we require diameter also. So diameter of the fin is 0.1 meter. Heat transfer coefficient is 10. And K values, as we are considering 3 materials. So this is K value for copper. This is K value for steel. This is K value for aluminum. So 3 values we have considered. Now, first of all, we obtain or we write the program for copper. So now X values are, because X is the length of the fin, it's Xi is equal to 0, Xf is equal to 1. You can write XL also here. No issues. Any notations you can use. Only the typical Greek symbols are not available. So that's why instead of theta, we are using Y. Y we are using. And bracket term is at particular one. That is a base. So again, here we are considering base temperature is 100 degrees Celsius. So theta 0, which is also called as a theta 1, we can say. And instead of theta, we are using Y. And this 1 is for the first case, that is for the copper. So you understand that. And M value, we write the formula of HP by K. And P by A is the hydraulic mean diameter, which is D by 4. So accordingly, we write the expression of M, where it takes value of M. It calculates M using the HTC value, K1 value, and diameter values. So these are the given quantities you can write, like we solve the numerical. Now, in this case, N value, while solving analytical, for simplicity, we have considered N value 6 only, step size. but here we are considering 60, 600, anything we can, because we don't have to solve it manually. So no issues. So higher the values of n, more accurate are the results. So that is the beauty of this numerical analysis. We can take the n values, anything, any higher values. Now here n is equal to 60. So step size, now here we are using the notation of step size as h instead of w in analytical. Here we are using h is equal to xf minus xi divided by n, that is the step size. So that formula we have written. So we have used p also in this matrix. So some coefficients, there are p values. So how to calculate that p value? So we write the expression of p also. Then the x, that is variation, that is x varies from xi to xf with interval h. So that is the step size is h, so that we have written. Now we have to write the matrix. So first we write the matrix, that is A zeros, all zeros for simplicity. That is, we are considering n minus 1, n minus 1, because that matrix is of 5 by 5. So 5 by 5 matrix we consider. So if step size is 6, that matrix size is 5 by 5. So as per the numerical, we can say. So for simplicity here, 60 means 59, 59 matrix, 59 by 59 matrix. But for simplicity, we take the same analytical value of n, that is n is equal to 6. So it is 5 by 5 matrix. So the result of this particular command is a zeros, a is equal to zeros, n minus 1, n comma, n minus 1 is this. So in your case, if you display this, you will get 59 by 59 matrix. Like similarly, b n minus 1 0. So to n minus 1, that is 5 rows. So there are 5 rows and only one column. So that is the interpretation of B matrix, all zeros. So this is B matrix. And if we put B1 is equal to minus y1, that is theta B, we can say. So we can have this. Okay, so this is the value addition. This is the command, or the result of this is it adds this particular value here. So this is a B matrix, we can say, and A matrix, but we have various coefficients here. So we that coefficient is for, again, I is equal to 1 to n minus 2, that is 1 to 4 matrix. So 4 by 4 matrix. So for I is equal to so I by I comma I, that is again 4 by 4 matrix. So this is the matrix we can say. So where is equal to minus p. So here I 1 comma 1, I 2 comma 2, I 3 comma 3, I 4 comma. So the result of this particular command is it can add minus p here up to this case. Then result of I comma I plus 1. So that is the first row and second, that is second column. So the result of this command is this. And result of third command, that is the second row and first column. So it puts one values here in previous for this and one value here it is. Now this is remaining. Now here we can end this particular matrix. So in order to get this value, so we can write a n minus 1, because this is only for this 4 by 4 matrix. So wherever we consider. And now we write the value here. So in order to write this is actually 5 by 5, we can say. A n minus 1, comma n minus 1. So that is 2 by p minus p. So with if we use this command, it puts the value. So this way a matrix is completed, whatever the coefficients we have to write. So all the coefficients we can write here by using this command. Then we can display matrix A by display command. Matrix B we can display. And now we have to solve this matrix. So that is the matrix size is this. So this is a matrix size because it varies from 2 to n. So n value is 6, suppose. In our case, it is 60. So 2 to 6 values, and only for a one column. So this is the matrix size. That is, this is the definition of theta matrix. That is equal on right hand side. It is inverse A multiplied by B. A inverse B. So this is A and this is B, suppose we can say. So this is B. So this is B. And theta 7 value, which is already also given, because theta 7 we have, because one of the equation we require this theta 7 also. So theta 7 value is 2 theta 6. So that is theta. So this one indicates that is we are treating the first case. This is for copper. We can write YC also, no issues. Y1 I have written it. That is 2 theta 6 by P. So this, because theta term is not there in Scilab, but this symbol is not available. That's why we, instead of theta, we are using Y. So for this, we have written. So now all the definitions, all the expressions we have written here. Now we can display this, all the values. Now this is the program for copper, and similar program we can write for the steel and aluminum. Only thing is that the values of K is different. So suppose if you have to write for steel, so instead of K1, it is written as K2. Rest steps are same, that is batch size, P values, X variation, then A matrix 0, B matrix, then for, so remaining steps are same. Only the change is there, that is Y2. So instead of Y1, it is, this is theta 2, we can say. Theta 2 is for steel, and the rest steps are same again. You can say again it is Y2. So this is about steel, and same you can write for aluminum. Again, here is slight printing mistake. It is not K2, is K3, which here we can take. And the same programs we can write here. So same steps we can write, only Y3. So, and finally we can take a plot of X versus Y1, that is for copper, and we use the marker. Then X versus X is the distance from the base, that is the length of the fin, we can say. And Y we can say is theta, that is the temperature difference. So Y1 is the temperature difference for copper, Y2 is the temperature difference for steel, Y3 is the temperature difference for aluminum, all these things. And these are the markers used. Then we can write the title by using X title command, write the label. X label is length of the fin, Y label is temperature difference. And after executing the program, we arrive to this. So first, this is for copper, this is for aluminum, this is for steel. As per the legend values, we already using the markers also. So we can see the analysis part, the copper temperature variation is not that much. It's a slow variation. So obviously heat transfer rate for copper is highest, followed by aluminum, followed by steel, because the K values of copper is maximum, aluminum is minimum. So we can get, so this particular profile is the best amongst all, because it provides the higher delta T across the length. Obviously, that is T minus T theta. So that's why this is the best amongst all as far as the heat transfer point of view. That's it from this experiment. The learning outcome of this, you could able to explain the governing equation for heat transfer analysis through fin. Then best part is the new part, that is you could able to describe how the finite difference method approach is implemented, especially central difference method here. Then how to write the program for solving matrix, especially for temperature variation along the length, and then how to analyze the plot variation along the length. So many materials you can use. That's it from this particular experiment. Thank you very much.